So this is the second part of this lab, the many faces of the reverend Bayes. Last time we talked about the use of Bayes' theorem in sort of the actual setup of machine learning. And this time we're going to go a little bit deeper into the statistics that's involved in Bayesian statistics. But so before we start talking about that, let's just recall what frequentist statistics actually is. In frequentist statistics, the basic idea is that you have a true but unknown parameter theta that you're trying to find, and that the data set that you actually have is not considered to be something that's constant. In the sense that you actually have a population, and from the population you've been given a sample, and now you've got to make some estimations about the population from the sample. In other words, there is a true parameter theta star that characterizes this population. We don't have this. We have a sample, and we can get theta hat instead. So one way to think about what's actually happening out here in frequentist statistics is what we did in that learning models lab that we did back. We basically drew different samples from the population because we had the population. We don't get that choice always, right? We don't have the population, and so we have to make an inference just based on a single sample. But the way we sort of play at having the population, or at least play at having different samples, is to use Bootstrap and create these different samples and then make some sort of inference on the value of theta and the value of theta hat that we found. Okay. So very normal, and you've seen this in the machine learning chapter where we talked about logistic regression. Very normal kind of way to do this is to use maximum likelihood, and the maximum likelihood idea is basically it's to find the parameter estimates that maximize the likelihood. So you write the probability of getting the data given the parameter, and you have like maybe n such values of your data. There are n such observations. You assume they're independent. That's and they're identically distributed. That they're coming from the same distribution. That's what IID means. They are independent and identically distributed. Then the likelihood is basically just a product of the probabilities for that data point to have come from that parameter. And then you multiply that, and you basically maximize this. You find the theta which maximizes this. Now, notice what's happening. It's taking each and every point that you have out there into account. Because it's taking each and every point that you have into account, the maximum likelihood method is a method that's going to typically overfit. And that's why when you train logistic regression using the log loss, which is just minus log p, so it's minus log of the likelihood, basically. That's the log loss that you use over there. So when you train logistic regression using that, you're going to, if you have a lot of features, you are going to overfit, and that's why you use some kind of regularization, either an L2 ridge regularization or a lasso regularization or something else, so that this overfitting doesn't happen. The Bayesian approach is a little bit different. In the Bayesian approach, we treat theta as a random variable, and we fix the data set. So we don't go about saying, oh, this is just one sample from the whole population, blah, blah, blah. We say that's the data set, and that's the end of the universe. That's all we know about it. We have this data set. So we don't talk anymore about the data set as a sample from the population, basically. So what we then associate with the parameter theta, some kind of prior distribution for that parameter. So this prior distribution represents a belief on the parameter values. We haven't observed any data yet, remember. It just basically turns out to be this kind of belief in what's sort of there on this data set. So in a Bayesian context, the parameters, the data is fixed, the parameter is changing. Remember, in the frequentist context, theta is fixed but unknown. In the Bayesian context, theta is actually random. It's got some distribution. And that's what we'll try and estimate. In a sense, both of these methods do have, even though they're like so different and hyped up to be so different, they do have a similar flavor. Here, basically what you're saying is that I have a distribution of thetas. And in frequentist statistics, you're saying, oh, I'm actually going to take the one sample I have, I'm going to bootstrap it and create many samples. For each one of those, I'm going to fit for a theta, and then I'm going to have some distribution over thetas. But in both cases, at the end of the day, I'm getting some kind of distribution over thetas. Even though in the frequentist case, theta is assumed fixed but unknown. To do inference, I need a distribution. Okay. So in the Bayesian context, the goal is to estimate what's called a posterior distribution. And the posterior distribution is basically the notion of what's theta given the data. And to do this, we rely on Bayes' theorem, which you can see written out here. And it says that the posterior distribution of theta given the data y is the likelihood, the probability of y, given the data theta, times the prior distribution for theta, divided by the probability of y. This is just Bayes' theorem written out in a different fashion. Now, there's an identicality between these two approaches if you put that p of theta is equal to 1. Then you see that all your and p of y doesn't depend on theta. So if you're then kind of sort of going to maximize the probability of theta given y by differentiating with respect to theta, you are differentiating the likelihood. And so that's the sort of equivalence between the two methods in formulas. So notice that this is a distribution over parameters. And there are some calculations we can make from it. That denominator up there is what's called the evidence, this denominator here. And it's basically just the probability of the data. So essentially, it integrates the numerator all the way through. Right? It's just a sum of all possible values of theta that could have happened. And what's the probability of the data given all these possible values of theta. Notice that it's weighted. It's basically the likelihood over here, weighted by these different priors. So if this prior was flat, this is basically a sum of likelihoods over the parameters. So the posterior distribution gives me a distribution on theta, on my parameters. But that's really not what I'm interested in. What I'm interested in calculating is making predictions, right? I want to make predictions that here's a new data point, y star. Make some kind of prediction for it. So what's the probability of this particular data point given the existing data? So in a machine learning context, this whole model might refer to a regression model. And you're trying to say, OK, I fit this regression model on n existing points. Now here's a new point, x star. And on this x star, I'm going to have some y, which comes out. And what's the distribution I get as a result of that? Now this distribution is called the posterior predictive distribution. And remember that it is a distribution. It's not a point value, right? And so what we're doing is here, we're now taking, instead of the prior, which was over here in the evidence, we're taking the posterior, and we are integrating it with the likelihood at the new points. So you can imagine that y star is some test set, if you like. And so we're taking the posterior at that, the likelihood at those points, multiplying it by the posterior probability for theta, and then summing up over it. So in a sense, this prediction is this a really good way to do predictions? And why is this a good way to do predictions? It's a good way to do predictions because you are not taking a particular value of theta. What we've been doing so far is that we've been taking a particular value of theta, let's say this value, and then we've been putting it in some formula, basically, to make a prediction. Here what we're doing is we're saying we have some distribution. So this is some distribution over theta. And you're saying that I want to sort of predict some new points that we have. And so you're taking this distribution and you're convolving, if you look at that formula, you're convolving this with the likelihood at those new points, basically. So, and then you're summing over all of this theta. So in a sense, you're taking your prediction and you're kind of smearing it out. And why is smearing out a good thing? Smearing out is a good thing simply because it's not the process of an optimization. It doesn't have a chance to overfit. By taking the signal, which is there in the wings of this distribution, of this posterior distribution, and putting that in by doing this integral, notice that you're doing this integral over all values of theta, and therefore all values of this. You are bringing in something from the tails over here. You're not just getting the value here. You're getting all this stuff in along with it. And so you might be a little bit less, sort of concrete in your answer, but your answer is much more likely to be correct. And much more likely to be not overfit. So this is sort of the point why doing things in a Bayesian way is a good idea. Having said that, many times you actually want to get a value from a distribution. You don't want this distribution. You're talking to your boss. If you give the boss that distribution, the boss might be confused. So you typically want a value. And the process of getting a value from a distribution is what Joe talked about in class the other day, and it's called decision theory. And we make some of these decisions so kind of blindly that we don't even think about it. But one such decision is, oh, I have this distribution, and all I'm going to get from this distribution, all I care about is this value. Whenever you do something like this, your bell should ring off in your head, overfitting, because you're just choosing one value. But at some point, if you're going to make some calculation, you might want a value. And you say, OK, I'm just going to take the maximum of this distribution. Another idea is maybe I'll take the mean of this distribution. Another idea maybe is I'll take the median of the distribution. So that's the ways of coming up with sort of like a point. But the maximum value of the distribution is what's called the maximum a posteriori, or the MAP estimate. And it's kind of similar to the maximum likelihood estimate, in which case in maximum likelihood you maximize the likelihood with respect to theta and got an estimate. Here you maximize the posterior with respect to theta, and you get an estimate. And these estimates need not be the same unless the prior is completely flat. If the prior puts some information into it, then these estimates will change from each other. Okay. So having sort of set this up in this kind of general fashion, we've talked about this notion of a posterior distribution, which is the distribution for theta. We've talked about the posterior predictive distribution, which is the distribution for new data. And so let's go and actually see some examples of this game. So this first example is from the book that Joe's been talking about in class, which is this Probabilistic Programming in Bayesian Methods for Hackers book. And it's an example of a binomial model. Now, a binomial model is basically, coins tossed, essentially. You have some probability p. Usually for a coin, it's like, half the probability to get heads and half the probability to get tails. But it could be some other thing. It could be a weighted coin of some kind. But you have two possibilities. That's your binomial model. And you're now trying to set a prior for this binomial model. So again, what you're doing over here is you have a binomial of n choose k. That's your likelihood. Your prior, according to conjugate priors, is a beta, which is a two-parameter distribution. And remember that beta of 1, 1 is a uniform distribution. Okay? And so when we multiply the likelihood of the binomial with the prior, essentially, we get a posterior, which is also a beta. And so the posterior is also a beta. And specifically, it's actually beta of, and it depends upon these. Let me not get it wrong, so I'm just going to look at it in this thing. Here it is, over there. So it's k plus, in this notation, it's basically k plus alpha and n minus k plus beta. And so that's the distribution that pops out of it. So how is this a useful thing to see, and what does this exactly mean? Well, you can think about the beta distribution as basically saying that if you look at this, and if you look at this sort of like similarity between the way the binomial is written and the beta is written, you can think about this as your prior as saying is that there were, out of alpha existing tosses, beta of those turned out to be heads. And then I threw the coin, I actually got my data, I did n tosses, and k of those turned out to be heads. And after that, the distribution I get is out of k plus 2, out of these n plus alpha things, I get k plus 2 as alpha, and then n minus k plus beta as the new kind of beta. And you can see that this is the number of heads that you started with, and that's the number of tails. So basically, I actually said that a little bit wrong earlier, that alpha is not the number of trials, it's the number of heads, and beta is the number of tails. So my apologies for that. Whereas the binomial is a little bit different. You could think of the binomial kind of reparametrized as k heads and n minus k tails, if you wanted to. And that would be the equivalence of these distributions. Okay, so let's actually do this. What we're doing is we're going to have a prior that we put in over here that is, and you can see over here from this formula, a 1, a beta of 1 and 1. So that's a completely flat prior, and you can look at this in this diagram where I have this flat prior I start with. I've started with no tosses, and I have observed no heads. And then I did it once, and I got 1 head. At this point, your maximum likelihood estimate would be that everything is a head. So it's clearly wrong. So maximum likelihood is not a good thing to do over here. And you do 2 tosses and 1 heads, and yeah, okay, so now you get the distribution peaked at 0.5 again, as you might expect. And you do 3 tosses, you get 1 heads, and it's moved to the left because you're thinking, I'm not getting many heads in this. And you do 4 tosses, and I still got 1 heads, as you know, in these things that happens. And you're going even more to the left because you're thinking, maybe this coin's actually biased. But then you keep doing this again and again and again and again. Here you come to 15 tosses, where still have only got 5 heads. But by the time you come to 50 tosses, we've gotten a little bit better. In fact, we've gotten to 27 heads and moved over the other side. And we've gotten to 500 tosses. And we've got about 243 heads. And you see you're very close to sort of this 0.5. You're not exactly there, but you're close to the 0.5. And that's because in these long amount of coin tosses, you're not going to get them exact, right? And this is what this is showing. But suppose I chose a prior that was not this 1-1, and I chose a rather skewed prior. Look at the prior I chose. Notice I have an A and a B over here, and I set the A to 5 and B to 20, so I have like 5 heads and 10 20s as my prior. I'm sorry, 5 heads and 20 tails as my prior. So I start off with that, and you can see the distribution I start off with. With 5 heads and 20 tails, that's 5 out of 25. You know, that's the prior is peaked somewhere over here, essentially. And now I keep tossing coins, I keep tossing these, and it takes a while. I mean, you know, over here I'm not doing much with 3 tosses and 1 heads to overcome this prior. But as I finally get to many, many more, here's 50 tosses and I get 21 heads, you can see this entire distribution moving to the left, kind of the data overwhelming the prior. And then you go to 500 tosses and I get 259 heads, and I'm quite there. And you go to 1,000 tosses at 510 heads, and 2,000 tosses and 974 heads, I'm quite close to 0.5. So what's happening, essentially, is that as I go more and more and more over, the prior is being drowned. So this is the good thing about Bayesian statistics, which you should sort of understand, that if I have a prior, and that represents either my prior belief on the thing, or some kind of data, the prior is informed in some sense by some data, so it has some kind of notion about the globality of things. And then I actually let the data come in, and I let the data come in, and I let the data come in, and I run this, and I see what happens. And if I have enough data, it'll overwhelm any prior. So it's like saying if I do an experiment again and again and again, and I observe some result, even if my prior belief was that an experiment's not going to be true, then I have to bow down to the data, essentially. Okay, so as you can see, there is some sensitivity to the prior on this thing. If my prior is so much, so much on one side that I really need to be convinced, I'll obviously need a lot of data to change this. And so you can think about this sort of philosophically from your own perspective of how you think about things. But amongst statisticians, there is sort of like some disagreement about how you set priors. And some people would like you to set priors in a completely uninformative fashion so that you don't bias the procedure. To which other statisticians will retort that your choice of the likelihood model and all of those things is already biasing the procedure. So it's better that you communicate your priors in a good fashion, and then go on from there. Okay. So the model I'm going to talk about right now is the normal model. It's the normal distribution. You're familiar with this. It's the probability of y, given that you know the mean and the sigma, the standard deviation, and that's the model. And if you have n points, then the likelihood is basically you're just multiplying those n points together, and you get that. And you can take the product inside the sum over there. So you get this kind of sum thing over there. Now, let's assume that we know sigma squared. So it turns out that to do this whole prior posterior thing with normal distributions can be pretty complicated if you don't know both the mean and the variance. Then it becomes a normal inverse gamma function. We won't talk about that right now, but so if you know the sigma squared, basically, you can write the posterior. There's some prior, given that you know the value of sigma squared, some prior on mu times the likelihood. Okay? So, and the conjugate of the normal distribution is the normal distribution itself, and you can basically show that the posterior is this quantity. And it's an exponent. It's a normal distribution with these a and this b over here, where a is this, and b is this specific quantity out here. So if you look at these, things, that this is a normal density with 1 over square root of a playing the role of the standard deviation, or basically 1 over a being the standard deviation. And you can see how the standard deviation is this sort of if you like, weighted, average, weighted harmonic average of these existing standard deviations, where the data, as n becomes larger and larger, this term, is overwhelming this term essentially. And if you had very little data, then this term would be kind of important in that standard deviation. And then you can think about this as the mean as this term divided by this term, right? It's b by a, basically. So that's the mean of this posterior distribution. And you can see that this mean of the posterior distribution can be written slightly differently. And if you define kappa to be sigma squared by tau squared, i.e. the ratio of your data's sigma to your prior standard deviation, your data's variance to your prior standard deviation, then you can write the mean. You can just take this formula over here, the b by a, and write it in this particular form. Okay? And straight away you can see that this is of the type that Joe talked about in class, where if you call this w, right, then this is 1 minus w. So it's this kind of weighted average of the prior mean and the sample mean, as you can see out there. Now, obviously this depends upon which one of these is bigger, right? If kappa is very large, you can straight off see that if kappa is very large, then your data distribution, your data variance is much more than your prior variance. And for a large kappa, basically what you're doing is that this term goes out, right? And your prior becomes important. So that's what's saying that if my data is not telling me anything, it has such a large variance that it's not telling me anything, my answer is going to come from my prior, right? So that's kind of the point over there. And the other side of it is that if kappa is small, i.e. that my prior is, I have been uninformative and I've kept my prior kind of, very spread out so that my tau is extremely large. And my data is actually converging to some kind of, smaller sort of distribution. Then you can see if that's the case, then kappa is small. And if kappa is small, you can see that this term is going to dominate and you're going to go towards the mean. But so depending upon what the ratio of these two things is, how far you go towards the data mean and how away you go from the prior mean. Okay. So here's an example of which I took from the AM207 notes, which is from moth wings. And we have data on the wing length in millimeters of 9 members of a species of moth. And here's that data. And it has an average of 18.14. And we've looked at the literature, and the literature has told us that other studies show that the wing length of these moths is about 19 millimeters. And we know that the length must be positive. So we can choose a prior now. We know this wing length to be 19 millimeters, so it's like something around 19. And we'll choose it fairly uninformative. We'll say that, okay, it's 19 plus or minus 10 in the standard deviation. So this is a fairly sort of like wide prior distribution. Okay? And now we have these measurements. And so we can get the sample mean over here, which is the y bar. And we can get kappa, basically, and we can find the posterior. So let's just do that over here in code. Here's the data. Here's the prior mean. Here's the prior standard deviation. And I can calculate the posterior basically as a normal distribution with a mu posterior and a sigma posterior. And this mu posterior I calculate using that formula that I showed you above. And the sigma posterior I also calculate using the same formula I showed you above. And now you can see what happens. This big swath all over here is the width of that prior. And now with those 10 points of data, you can see how much peaked and narrow the posterior is, telling you that the average value of the moths is somewhere over there. And you can check what its value exactly is, what the peak of this is. Okay. So that's an example of something with a relatively uninformative informative prior. Let's look at an example where the prior is much more informative. So this is the data set. This is the example that Joe talked about in class. It's a data set about counties in the U.S. and the kidney cancer fatalities they've had over 5 years on a per county basis. So it's stored in this where the fatalities are stored. So for example, Baldwin County in Alabama had 15, but Otago County just had 1 fatality over 5 years. Okay, so the population is the county population, and the 5-year mortality is calculated by dividing one by the other over there. So let's look at what this looks like. And here I have some code for you to be able to plot maps, which might come useful. But I'm going to not talk about it right now. So what I'm going to do is I'm going to take my data frame. I'm going to sort it by this 5-year mortality. And I'm going to get the top 323 counties. And I'm going to plot these 323 counties. And you see these. counties. And as Joe talked about in class, it turns out that this is the case because this is not the case because people have bad access to hospitals or something like that in the Midwest. If you plot the bottom counties in red and the top counties, and you just plot them both on a map, you can see right next to each other that they're just kind of like next to each other, but in the same kind of areas of the country. There's very little in California. There's very little on the East Coast. And you might say that this supports the kind of notion that it's places where there are no cities, and you might have a point. But you'll actually, if you were to, and I should have done this, but if you actually plot the population, since I have it as well, you'll see that these are all low population counties. And you can actually check this on another plot that we'll make over here. Oh, by the way, before I make the plot, I'm actually going to get the per year mortality rate by just dividing the 5-year mortality by 5. And so then I'm going to store it in the variable rate, and then I'm going to plot this rate against population for each of these 3 sets. So for everybody, it's plotted in gray. For the top, for the top kidney cancer, it is plotted in blue, and for the bottom kidney cancer, it's plotted in red. And you can see that what's happening is that these blues and these reds are basically happening at low population, at low populations, less than 100,000 people. The counties where you have more than 100,000 people, it's not terribly clear on this because I chose to use gray, but you'll see this band extend like this, and it's a fairly narrow band actually. So at this point, your job is to sort of kind of get some notion of, in a county like this, what's the true kidney cancer death rate over here? And what are you to do this? Okay, so this is a great place where using Bayesian techniques comes in very useful. So the structure of priors is where this kind of becomes important. Clearly, you have this kind of notion that in counties where there are lots of people, so that I have some kind of notion of statistical strength, that the rate is somewhere around here. So this is information that I should somehow use to give you answers on this. I mean, yes, there's a low rate here, but I should somehow regularize that information with the information that's here. This is, by the way, the same regularization you saw in machine learning. It's not any different, and I'll show you in a second why it's not any different, but it's exactly the same idea. It's like you're borrowing statistical strength. You're saying, I don't want to overfit by taking these counties just because they have low populations, and I don't know much about them, right? I mean, you can see what happens in this county. If you have 1,000 people living in a county, if you have 1 death in 1,000 people, that's a lot of deaths, and if you have 0 deaths in 1,000 people, that's very little deaths. And so, but then you're overfitting to that county per se, and you don't want to do that, so you want to get this information from the overall mean. You want to regularize these estimates here and these estimates here. Okay, so what can you do? One thing you can do is full pooling, right? You can just take all the counts and the populations together over the nation, estimate one death rate, and say that this is the death rate everywhere. So this should remind you of bias, right? This is like a bulldozer. You're saying everything is this like one flat death rate everywhere. And you're like, okay, that's not the smartest idea. The other extreme is what we've been doing, right? We've been saying that the death rates are exactly what's plotted up here. That's where 1 for each county, and this is your variance limit, right? This is where you said, okay, that model is kind of useless because it doesn't tell you anything about what the death rate is likely to be. So the model you want, as usual, with anything in statistics and machine learning, is the one which sort of takes care of this bias variance trade-off. So the idea is to borrow statistical strength from the overall average while not accepting it entirely. And the way you do this is from this kind of concept of what's called a hierarchical model. So what you do in this hierarchical model notion is you take all these county units, and we're going to model these county units. The count of deaths is a Poisson distribution in each one. So this is a Poisson with some sort of rate parameter lambda. So lambda 1 over here, and then it's lambda 2 there, lambda 3 there, lambda 4 there. And this gives you the actual rates. And over here it might have been 0, and over here it might have been 1, and here it might have been 15, and here it might have been 3, and so on and so forth. These are your various county units. Well, you now say that these lambdas are coming from a gamma distribution. And the reason you use a gamma distribution is simply that the gamma is a conjugate prior of the Poisson distribution. You know you've done too much Python when you say the Python distribution. So this is gamma of alpha beta. And you say that each one of these lambdas is a draw from this distribution. And that's why you have this, sort of like difference between these various lambdas over here. So I draw it from here. And so you can see what happens since these are conjugates. My actual values, the posteriors, are also going to be gammas. So now those are going to be the actual values I get. And I'm going to take these gammas and whatever rate I get out here, I'm going to compare it to the mean of this gamma distribution rather than that rate parameter that went inside the Poisson distribution. And because I'm borrowing statistical strength from this kind of pooling that I'm doing over here, this is called a hierarchical model. And because I'm borrowing the statistical strength from this pooling, I won't get the big variation that I'm getting in rates, right? So, 15 over 5 years or 3 over 5 years, and so on and so forth. Well, 15 over the population over 5 years. And so that, I should just very quickly mention that 15 that I was talking about, which comes from, say, Alabama's Baldwin County, is actually kind of large, because look at this. This is 64,915, and I have 1 death, and it's about thrice the size, and I have 15 times the deaths. So, that's a county where there's lots of deaths. Okay. So let's create this partially pooled model. So what are we going to do? We're going to say the likelihood is a product of Poissons over the counties. Each one of these has a different rate parameter, and the rate parameter is here. And I've parameterized it in this interesting fashion. Because remember, in the Poisson distribution, this needs to be the mean. So I'm saying that I have some rate theta per year, per person kind of rate. So since it's a per person rate, I'm going to multiply it by the number of people. So that's going to be the per year rate. And then since yi is the number of deaths in 5 years, I'm going to multiply by 5 years. That's why this parameterization is of this particular type. And then I'm going to say that the probability of theta j is going to be a gamma of alpha and beta. And I'm going to multiply this together, and you'll find that this is a gamma of alpha plus yj and a beta plus 5nj. And you can check this out from the products of Poisson gamma distributions. You'll find there's a great Wikipedia page on conjugate distributions, which you should take a look at, and which is worth looking at. So remember, to calculate this particular posterior, we have, remember that the likelihood had like over, say there are 3,000 counties, had 3,000 Poissons multiplied. But I'm only talking about the gamma, notice the proportional sign, I'm only talking about the gammas that correspond to the jth county. So really, in the joint posterior, there is all this other stuff. But I don't care what this other stuff is. I can just integrate over it, and I can say, I can do what is called marginalization. And the marginalization basically says that the posterior distribution is for all of these. So it's product over I, P of theta I, given yj, and some prior distribution of the theta i's, right? Which is this gamma distribution. So what I'm doing out here is I'm saying, well, let me just split it out. Let me say I not equal to j and multiply it by the jth county. So that's theta j given yj times p of theta j. All of this I don't care about because it separates out so nicely. So that's what I'm going to say, that this posterior distribution is just proportional to this part. Sorry, this should be yj given theta j. I'm a little bit out to lunch. This is the likelihood. yi given theta I. yj given theta j. So this is the entire posterior, right? The posterior of the theta 1 dot 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 theta j dot 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 theta n given all the y's. yi dot dot dot. And I only care now to find the posterior of theta j given all the y's. And then I can write that posterior as this term over here multiplied by the rest of the stuff, and I don't care about what the rest of the stuff is. But to write the posterior specifically, what I need to do, since I should show you what this formalism is, y1, yj, yn is equal to integral d theta 1, d theta 2, d theta 3, bunk, 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 of that entire posterior distribution I had earlier. Theta 1, theta 2, given y's, given the set of y's. So that's what I'm doing, and I'm taking this out. And it doesn't matter to me because the only one I care about is the theta j, so that pops out. since these posterior distributions just multiply, and then this entire integral just becomes a constant. And that's why I have this proportionality over here. That's why it's just proportional to the likelihood of just that j times the prior for that j, and the rest of it is integrated out. And I don't care about, it's a constant. I don't even have to calculate that integral. Okay, so this is one of the 3,000 different posteriors. Actually, there's more than 3,000 posteriors. There's the posteriors for that, and then there's a posterior for alpha, and there's a posterior for beta, which come from the gamma distribution. So there are posteriors for all of those things. So there's alpha plus beta plus how many ever counties you have, and since we are calling them 3,000, it's 3,002 posteriors, of which I only want to find one posterior because I only care about county j. So that's what I'm doing here. And usually to do this kind of thing, we need to do, and I'll put in some text on that over here, but to do a full Bayesian thing of the model, we usually use something called MCMC sampling that Joe talked about a little bit, in which case we have basically a distribution for each one of these parameters. The 3,000 parameters are easy. They're just gamma distributions. You don't need to do any MCMC. You go to scipy.stats, you get the gamma distribution, you throw it. But for the alpha and beta, it's much more complicated. You have to use a technique called Gibbs sampling to actually get the full Bayesian model. But there is a simpler Bayesian model that you can do, and it's called empirical Bayes. And there are different versions of it. One of them is to basically differentiate the evidence you saw earlier, which I shall, this formula was all the way up. So one idea is to take that evidence and just maximize that evidence with respect to theta, and that gives you some estimate of theta. This is called marginal likelihood, and this is one form of empirical Bayes. But an even simpler form of empirical Bayes, which we'll carry out over here, is this notion of using moment matching. And moment matching is a very, very simple idea, and let me just describe what's happening over here. So the first thing I'm doing is I'm saying that the mean of this posterior distribution, since I know it's a gamma distribution, I know the means and variances of gamma distributions is this particular quantity out here. So notice what it's doing. It's taking so the mean is basically of this gamma distribution is basically giving you these ratios, right? Since it's this ratios, it's this rate ratio that you're talking about, the rate. It's basically basically regularizing the rate by adding something to the numerator and something to the denominator. It's a very standard kind of notion of regularization that you've seen before. So it's taking the yj over 5nj death rate, and it's regularizing it by this. So that's the mean of the posterior distribution. That by itself is just going to give us the rates, and we write a little lambda function to capture that. But then we're interested in the deaths. Remember, we're not interested in the rates per se, but we're interested in the deaths in every county. So to get the deaths in every county, we need to predict. So let's, for a second, think like we're predicting at a new county. So for that, we need to get the posterior predictive distribution. So what we do is we find the posterior predictive distribution, and it turns out that if you have a Poisson likelihood and a gamma prior, then you get a gamma posterior. And that gamma posterior, when you integrate the gamma posterior again with the Poisson likelihood at these new points, right? That's what we do to find the posterior predictive distribution. Let me just quickly go back to that formula right at the top over there. Did I go too far? No, here it is, this. So you're taking the posterior distribution, the gamma distribution, and integrating it against that Poisson. That's going to give you a different distribution. And the distribution we get, and again, you can look this up on Wikipedia. They have an incredibly good page, is what's called a negative binomial distribution. And those are the parameters of the negative binomial distribution. Okay. So this particular negative binomial, the negative binomial distribution, and remember, you're doing this for every county j. So this particular negative binomial distribution has a mean and a variance. I shouldn't have put the averages around there. Let me just fix that while we're at it. And you'll understand why I'm doing that in a second. So for each and every county, we have this negative binomial distribution now. It's the posterior predictive distributions. We have 3,000 posterior predictive distributions. For each one of those, that's the average, and that's the variance. Well, this average in the posterior predictive distribution is going to give us the number of deaths in that particular county. Now notice that we don't know alpha and beta. This was the whole idea. And normally if you did this in a full Bayes way, we'd actually do an MCMC or a Gibbs sampler to basically get the alpha and beta. But here's the simple way of getting the alpha and beta. This is the number of deaths in each county. We have a number for this. Remember, we have an estimate of this that we got from the data, which was like 1 death in Autauga and 15 in Baldwin, and so on and so forth. So what we're going to take is we're going to take the deaths in all these 3,000 counties, and we're going to average them. So we're going to take this thing and average it in all 3,000 counties, and that's why I had that little average symbol over it. And I'm going to put it equal to the average in the data. So this is the way I'm kind of estimating the prior from the data. And this is the basic idea behind empirical Bayes, is that you estimate the prior from the data. So, you know, it's going to be NJ. If I remember, Autauga had like 64,000 and Baldwin had 193,000 people. I'm going to do that for all the counties in the country. Basically, I'm going to average it. I get the average number of people in every in all counties in the country. And I'll have the average number of deaths of all counties in the country. That's going to give me one equation for alpha and beta. Then I'm going to do the same thing with the variance. I have all that data, right? I can calculate the variance of those deaths as well. So I'll calculate the variance of the deaths, and I'll need to get the average of the NJ and the average of the NJ squared. And I'll have another equation for alpha and beta. I have two equations for alpha and beta. I can solve for alpha and beta. I'm home. Now, this is not as accurate an estimate, by the way, as you do when you do a full Bayes thing. But it's for a lot of purposes, it's enough. It does regularize the data. It does that part of it, at least. The exact values you get may not be particularly great because it's this kind of hokey approximation procedure. But if you want exact values, then you should do a full MCMC. And you'll learn about that if you take AM207, for example. So here's what I'm doing. I calculate the mean y. I calculate the variance in y. The mean population squared. And I use that to solve for alpha by beta over here. And then I use that to calculate beta. And I estimate A and B here, which are alpha and beta. And those are my estimates. Now, using those estimates, yeah, very quickly, I'll also show you this is what the prior looks like, using those estimates, alpha and beta, basically. And using those estimates, I'll redraw that diagram. So in that diagram, remember, I had the red dots, which were the underestimated ones, and the blue dots, which are the overestimated ones. The green dots you see out here basically are the new regularized estimates that I got. And how did I get these regularized estimates? What did I do? I'm looking for a rate, remember? And I can get the rate, essentially, from the posterior. So having estimated alpha and beta, I will get it. I'll use the posterior, which, remember, was a gamma distribution. And I'll use the means of that gamma distribution to calculate the rates. And there you go. There are the rates. And you can see what's happened is that these high and low values have now all come down and all got shrunk into this line over here, which is very close to the mean. And that's exactly what an empirical Bayes kind of idea is, that I'm actually going to set the prior using the data and use that overall kind of average from everywhere to sort of like shrink the values down, essentially. Okay. For those counties where, you know, there was enough data, so to speak, those counties are not going to get shrunk down as much. It's the kind of counties with very low populations and very high populations where you don't expect it, that's going to happen. Okay, so, and then what you can do is you can take these, you can take the observed deaths over here, and you can plot the posterior means over here. And this is what I'm doing over here, actually. I shouldn't have called that posterior means, because this is the posterior predictive mean. Remember, the posterior predictive is what gives me the number of deaths. Let's fix that. And you can see what happens over here, that this is the line of equality of the observed and the posterior predictive. And you can see that what's happening is that there is shrinkage happening, that you are being shrunk down towards being a little bit flatter on this posterior predictive mean. Remember, if you had just one value for all the counties, it would be a completely flat line, which is not what we want. Neither do we want each one to have the exact values, which would be this line, but it gets shrunk down between those two over here. And that's what empirical Bayes does for you. Okay, so very quickly, I'm going to run over a little bit of, I have about 10 minutes, right, of Bayesian updating and what this has to do with machine learning. So this is going back again to phase one. Remember, in the second notebook, I talked a lot about Bayesian statistics per se. And in the first one, I used Bayes' theorem to talk about predictions. But obviously, what you want to do is you want to bring these Bayesian techniques to bear on your predictions as well. So let's go to a model that we know and are very familiar with. That's linear regression. That's, you know, that y is equal to ax plus b plus epsilon. And what we're going to do now is to set priors on A and B. In this particular case, we'll just assume that B is 0, so we're not setting a prior on that, and we'll set a prior on A. And I generate some synthetic data here. That's the line I'm trying to fit. And what I'll do is you choose a normal prior, essentially. That's what the prior looks like. And you have a likelihood, which is a normal likelihood, basically, in this thing. What the likelihood is basically saying is that this noise out here, the difference between what is going to be your best fit line and these values is basically Gaussian distributed. That's the basic model in regression. And so you have a prior on that noise, and that's what that looks like. Actually, you have a sort of noise, and that's what that looks like. And then you say, I'm going to have a prior on the slope of this line. Should the line be like that? Should the line be like that? So basically, I'm going to sort of do a Gaussian prior on the slope of this line. And let me see how I set the prior. I set the prior to be at slope 0. And slope 0 would be a line like this, which doesn't look like this data at all. But that's the prior I'm setting. And I'm going to let the slopes vary a lot from there to here. So that's the game. OK. So then I got the prior. I got the likelihood over there. And then I multiplied the prior by the likelihood. So you see that's what I'm doing over here. Posterior is equal to prior times the likelihood in this little line here. Now, I need to be able to draw. So typically, you do this using MCMC techniques. But there's also a very simple technique to do this. It's called rejection sampling. And I just have a little bit of a show for what rejection sampling is. Basically, the idea is that this is going to be some distribution. The posterior times the likelihood. It's some funny-looking distribution. So what you say instead is something very simple. You say, well, what I'm going to do is I'm going to actually create a box which is around the top of this thing. And the lower the box is, the kind of better. And what I'm then going to do is I'm going to just basically throw darts at this thing. And there's a certain number of darts which will come below here. And those are the darts I'm interested in. There's a certain amount of darts that are going to go above here. And those are the darts I'm not interested in. And once I've counted all the darts where they fell, then I'm going to say, oh, the darts that fell between here and here, they're going to be those many. The darts over here, those many. The darts over here, count those many. And I'm going to basically create this kind of histogram which approximates this curve. And that's the game. That's what sampling is all about. MCMC is just a more complicated way of doing this. The reason that this is you want to do MCMC and not this is because making this box and then, you see how many points I'm rejecting. I'm rejecting all of these points. It's almost like a third or maybe more. It's actually really, really expensive. So that's why you use MCMC techniques. But that's all I'm doing out here. And the entire piece of code you can see is out here. Here's the dart throwing. Is basically generating points in a uniform distribution, and then throwing out everything which is above a certain amount. And when I do that, you can see what the posterior looks like. And it's, as you expected, it's going to be a Gaussian distribution. But this is one way to generate samples, essentially. So you don't need to do this, actually, for a normal for a regression case. Here is, taken again from the AM207 notes, the complete model. Including in multiple dimensions over here for the regression. I won't go over this model in any great amount of detail, but the important thing to know is that you're going to set up prior on the coefficients W, and you have some noise model for epsilon. In here, we've just called it sigma n as the noise, and it's normal distribution around 0. So what you're going to do is you're going to set a prior on the W's, and you're saying that the sum covariance matrix for the normal distribution, and it's all around 0. And then you do that, you multiply that, you get a posterior, you complete the squares, and you can look at the formulas, and you get the thing. The critical thing about this that I want you to take away, though, is that you have a prior on W, and that prior has some covariance matrix. Let's actually simplify that covariance matrix for a second and say it's just diagonal. Okay, so that there's no, the dimensions are not mixed up. So it's of the type alpha times I. It's a diagonal covariance matrix. And if you do this and you actually write the thing out, you'll find that you're going to get an exponent, right? And this is going to go into the exponent over there. And so you have two normal distributions. Let me just write this out for you so you can see this. So you have a normal distribution, and I'll just write it in one dimension to be kind of, to make it kind of simpler. And remember that for the prior W, I said there's going to be a kind of thing, and it's going to be like e to the minus alpha, and it was going to be w with a 0 mean, so it's going to be like w squared, basically. And so when I take these two, and this is my probability, right, my posterior, if I take minus the log of the posterior, then the e's go away, and I'm going to get x minus mu squared over 2 sigma squared plus, there's a minus up there, so minus, and the minuses also go away, plus alpha w squared. Now, this should remind you of the loss that you minimize when you do a linear regression. And this part particularly should remind you of the regularization term. And so alpha is the regularization term that comes in over there. So that's where, that's the sort of Bayesian equivalent to the regularization. So all of these regularization techniques, remember Joe saying that any frequentist method should have a Bayesian equivalent, the theorem. There you go. And that's how regularization comes into normal machine learning models from a Bayesian perspective. Okay, and normal sort of the posterior predictive distribution, by the way, of the linear regression model is also a normal distribution, so it's actually kind of nice. And over here, I have run through an example where I have some lines over here, some points over here, and I want to fit a line, and I actually go step by step. Here's my prior distribution. It's kind of a big distribution there. And these are the possible lines that I can draw at this point, you know, right at the beginning, because these are randomly drawn lines, because I don't have any points. Now, I have all the code over here, but you can see what happens is that first I just get in one point. And that one point basically says, well, you can't have all of these things. You could have all of these things, but it actually restricts, in your dimension here, by the way, is two-dimensional, because you have the intercept and the slope. So this is restricting the internet and the intercept and the slope to be in a particular kind of area. And the moment you give me 2 points, or 3 or 4 points, you see how much it has sort of like said that the slope's got to be quietened down. So you can now see that in this dimension, I am basically almost kind of set that this is what the slope's going to be. This dimension I'm not quite set in as yet. And so then I add more points. So what I'm doing is, all those points I had, I'm just bringing them in one by one. It's like a show. And I bring them in more one by one. And once I have even more points, then that slope variation has also gone down, and the intercept variation also goes down. And so this width is also coming to be smaller and smaller and smaller. And then as I go and add more and more points, you can see the posterior basically narrows down to a very small point. Remember, we saw that normal model earlier. It's exactly the same thing going on here. Is that over here my prior was very large, or actually this is not the prior in this particular diagram. That was a prior over there, extremely large. Here this is the first posterior after seeing 1 point. That's got narrowed down, but still it's all over the place. And then boom, by the time you have all of these points, you can see what lines will fit, and you can see the areas. You should take a look at the code. It's kind of fun to look at. So let me just close up by saying, remember we talked that there were multiple losses in machine learning. So the losses we've talked about here, including in this problem and that and the regularization thing I showed you, and so on and so forth, that's all the estimation loss. That's getting the probability distribution. That's how regularization comes in. You basically have this notion of having some maximum likelihood estimate. In the logistic regression, it's the log loss. Regression, it's this thing over here. And then on top of that, what you're doing is basically you are putting in some regularization, which comes in through the prior, and the prior may be determined from data, as we saw in the example of the cancers. Now, having done this, what we need to do is we need to use some kind of definition of what risk is, and we need to make decisions. And in this part of decision theory, remember again that there were 2 losses. The first loss was the estimation loss, which we talked about. The second loss is the decision loss that we need to talk about. So as you can see from this diagram, there are multiple regression curves. So in other words, what the regression model looks like is here's my points that I'm trying to fit, right? And I fit something to these points. But because this is a distribution, the posterior predictive distribution for a new x star over here is going to be a distribution over y. Let's call that y star, which corresponds to this thing, and I'll tell you what corresponds to means in a second. And so you have some distribution, and it's actually, as I told you earlier, it's going to be a Gaussian distribution. Now, it's a distribution. What point do I choose? Why did I choose this particular point? I chose this particular point because it's a Gaussian distribution, and it's equal to the mode, equal to the median, and is equal to the mean. But choosing something in a distribution requires decision theory. It requires, how do you get one point from a distribution? And Joe talked about this yesterday. If you want to choose the mean, you choose L2. Basically, you choose your decision loss. Remember, your decision loss, not your estimation loss, as y minus g squared. If you choose L1, then you get the median. So that gives you the mean. And so absolute value of y minus g gives you the median. Similarly, if you're doing classification, you can choose different losses. You can choose, as we have done before, you can choose the 1-0 loss, and that gives you accuracy as a metric. If you choose some asymmetric loss, because that's your problem, like the profit problem in homework 3, then your metric changes. And in fact, you should use the metric which is normal for your business problem. Many people say that the Gaussian model, so a lot of people who will tell you that a Gaussian model has this loss and this decision loss because it uses a Gaussian. That has nothing to do with it. There are two separate losses. There is the squared loss, which comes into the estimation loss, which was the x minus mu squared over 2 sigma squared plus the alpha w squared kind of thing you had. So that's the estimation loss. And the decision loss is completely your choice. So anybody who tells you that the decision loss is the squared because of this is confusing the estimation loss and the decision loss. You can have this estimation loss and choose y minus g as your decision loss, and that will give you the median of the distribution. So that's one point I wanted to make clear. There are multiple risks, multiple losses, and remember that average risk, as Joe said yesterday, loss is what you do on a point-by-point basis. Risk is what you talk about when you average it, and I have a little bit of code that shows you and goes back over here to the stuff we did on the homework and in the lab on the churn problem and how some of these things come about, both for regression, for classification, for hyperparameters, for cross-validation, and so on and so forth, but I'm out of time to talk more about that. So this part is worth reading. It actually sort of explains why machine learning the way it is. And I will combine it later with sort of a lab on profits, which I owe you because of some of the questions that have arisen on homework 3. And you'll see the entire structure of risk. But if you are mathematically inclined, it's really worth reading this last section. It gives you a notion of the differences that we started this lab with last time, the sort of empirical risk framework versus the probabilistic framework. And I'll just add one line to finish this, which gives away some of the story, that usually what you're doing is that you're using the probabilistic framework for the estimation loss, and then for the decision loss, you're always using some kind of empirical risk framework. If you're doing an SVM, then you're using an empirical risk framework all the way. Okay, thank you.